So, hopefully, you have your notes from last class so that you can see what we were doing at the end of last class, because we're going to do pretty much a continuation of that. If you look at your notes from last class, we were learning how to do equilibrium problems using what is called an ICE table. Do you remember that? Yeah, a little bit, maybe a little bit. Okay. First of all, yesterday at Cougar Time and after school yesterday, I kept getting the same question over and over again, which is a really good question. People were asking, how do you know if an equilibrium problem requires an ICE table? Because they all don't. Some do, some don't. Awesome question. The way you know is when you read through the problem, if you are given information about the initial conditions, remember that's what that I in ICE stood for, initial. You're given initial conditions and you're also asked something about the equilibrium conditions, okay? Or vice versa, okay? The point is, if you have a problem where you are either asked something or told something about these two different situations, the before and the after, that is a problem that requires an ICE table. But some of the problems more towards the beginning of our problem set are questions that simply give you conditions at equilibrium and nothing else. There's no mention of initial or beginning conditions. Then you don't need an ICE table. Okay? It's only if you're presented with two different situations that you need an ICE table. And we're going to get some more practice with these ICE tables. You'll notice that at the top of the slide it says type 2. We did type 1 last class. Type 2 is really, the setup is no different, guys. We're going to set up an ICE table just like we did for type 1. The only difference is our unknown will be in a slightly different location. So we're going to look at this one together as a group, and then you're going to get some practice on your own. Oops. So the question says, let me go back, sorry. The question says, carbon monoxide reacts with steam to produce carbon dioxide and hydrogen gas. At 700 Kelvin, the equilibrium constant is 5.10. Well, that is our first difference between type 1 and type 2. If you go back and look at the problems we did last class, we had to solve for the equilibrium constant value. It was not given to us. This time it is. So there's our first difference right off the bat. And before even reading this next paragraph or this next sentence, we need a reaction. Okay, we need to write out and balance our reaction, and everything is given to us in this first sentence. So let's do that. What is the formula for carbon monoxide? Okay, CO plus steam. What's steam? H2O. Carbon dioxide. CO2. And hydrogen gas. H2. Is it balanced? Yeah, it is. Okay, let's read on. Calculate the equilibrium concentrations of all species. Species just means all parts of the reaction. If 1 mole of each component is mixed in a 1 liter flask. Now, what I'm drawing brackets around, what are those conditions? Someone said it, say it. Initial. These are my initial conditions. I'm also being asked something about equilibrium. Does this problem require an ice table? Yes, it does. Okay. So first thing I want to do, I'm just going to copy down that equation so I can write something underneath it. I, C, E. Okay? Initial conditions. Initial what? What kind of numbers do we put in an ice table? Okay, molarities. Initially, I have 1 mole of everything in 1 liter. Nice, easy numbers. 1 divided by 1, 1 molar for each component here. Okay. What does C stand for? Change, okay? And last class we said most problems you can make an assumption about which way this reaction is going to move. Which way should I assume? All right, let's assume it shifts to the right, and I'll review with you how do you know if it's going the other way. So if it's shifting to the right, what should I write underneath carbon monoxide here? Minus what? X. All right, how about right here? Minus X here. Plus X and plus X again. And I'm just going to condense it down. Okay? Now, just keep in mind what this represents. These are the equilibrium molarities of each of these components. And that's what I'm asked to solve for. The problem is, I don't know what X equals. And if I can't find X, then I can't solve this problem. Any suggestions on how I might find a value for X? Yes, sir. Okay. Sounds good. Let's write that out and then we'll solve it. Meg, you are needed, sir. See what happens when you answer a question? I'm kidding.
They're all going to answer.
All right. Now, before I do anything with these X's, can you tell me what the equilibrium expression would look like for this reaction? Remember, expression means no numbers yet. Okay, Xander, tell me. Very good. Good, I'm glad you said times. I've seen a number of people writing plus signs in there. That's not correct. Okay? Very good. And I'm going to substitute in these expressions with X. And we were given a number. Now that's different than last time. We didn't have a value for K last time. Do you all see that I can simplify this just a little bit to look like this? Okay, now, I hear people already punching numbers on your calculator. Stop it. Just stop it. Okay? If you are at all concerned about your algebra skills or being able to solve for x in something that's relatively complicated, don't be, because I have a foolproof way to get x every time. This particular problem actually would not be that difficult to work out by hand. Do you all see I could just take the square root of both sides and get x that way? But I want you to be aware that although this particular problem has very simple numbers to work with, they will not always be so simple. Imagine, first of all, if these were not all 1 molar, and the coefficients were not all 1s. Then this could be like 4 plus 6x to the 6th times 3 plus 3x to the 3rd. I mean, these could get very nasty and very difficult to solve. So we are going to solve them by graphing them. Okay? So, do not jump ahead. Although this one is relatively simple, they are not always going to be so simple. Okay? So, let's just all stay together here. The first thing I want you to do is go to y equals, and for y1, I want you to type in y1 equals 5.10. For y2, we are going to put in this entire thing. Now don't start typing yet, because listen. Alright, as wonderful as these calculators are, they are not the greatest about obeying order of operations. So, in order to make sure that you type everything in correctly, you must, I'm using a capital M-U-S-T, put parentheses around your entire numerator and your entire denominator. If you don't do that, you'll get the wrong answer. So let's do this together. Type it all in. So character for character, what I have typed in, parentheses, parentheses, 1 plus x squared, parentheses, divided by, parentheses, parentheses. Okay? Now, fastest way to get to the graph, go to Zoom, and do number 6, Zoom Standard. If you did it right, your graph should look something like this. Does yours look something like that? Okay? And if it doesn't, I will help you. Alright, now I want you guys to notice that when we went to Zoom Standard, on this particular graph, we can see the intersection points. You will not always be able to see them, and that's okay. You don't have to be able to see them. Alright? Go to second and hit the trace button. What do you think we want? Intersect. Now, pause for 1 second. For any of you that have a TI-89, stop listening for 1 second. Just stop listening. For the rest of us, we're going to hit intersect, don't move the cursor, and hit enter, enter, enter. Intersect, enter, enter, enter. What comes up for x? Point what? If you did it right, that's what you should get. I know what some of you are thinking. There's more than one intersection point, isn't there? Okay. Well, couldn't x equal that other intersection point? Mathematically, yes. Chemically, no. All right? If you look at your graph, guys, I'm just going to sort of estimate what that other x value could be. Maybe it's like 2.7 or something. Okay, fine, 2.6. Imagine taking the number x equals 2.6 and plugging it in right there. What's the problem? 1 minus 2.6, that gives you a negative molarity. Do negative molarities exist? No. Okay? There is only one intersection point that will work, and this is one thing that I absolutely love about these calculators, and don't ask me how it does it. It's like the calculator and I we're in sync. We're simpatico. All right? For whatever reason, going intersect, not moving the cursor, enter, 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 always gives you the correct intersection point. What do I do with this number, 3.86? All right? So ladies and gentlemen, to recap here. Our ice table setup, our equilibrium expression setup, exactly the same as what we did last class. The difference between this type and the one we did last class, what I call type 1, is we used a different method to find x. Last class, we were given information about one of our components at equilibrium, so I could solve for x very easily. Did we do any graphing last class? No. Nope. Okay. Here, I wasn't given that information. I had to solve for x another way. And then from there, it's the same. Okay? So, somebody asked a good question last class. What if we go through this process, we do everything right, and the x that comes out is negative? What does that mean? Does it mean we zeroed in on the wrong intersection point? No. What does it mean? You got it. We made the wrong assumption up there. That means you need to change the direction of your arrow and change all these signs. Okay. So I want you to try this one on your own. Now guys, just a number of you already figured this out, but I just want to make sure that you all recognize this. When one side of your reaction has a 0 on it, we always make the assumption that it goes forward, but in this particular case, because that 0 is there, I don't have to assume. I can be 100% certain this has to move that way. There is no way it could move backwards, because then this would become negative. Impossible. If you did your graphing right, this is what should come up. I'm going to give you another one to practice, okay? Because I really want to make sure you get this. There is a slight little difference on the next slide, but it's the same process.
Pressure.
Pressure. Okay? Pressures. Ladies and gentlemen, this is the exact same type of problem. I'm given some initial conditions, I'm asked about equilibrium conditions, and I'm given a value for K, or Kp in this case. Do I need an ice table? Yes. The only little difference is instead of putting molarities into my ice table, you put partial pressures. The process is exactly the same. Except, in fact, it's even easier. Because on the previous slides, we had to divide our moles divided by liters. We don't have to do that. This is totally extraneous information. I don't need this volume at all. My pressures are right here, and I can take those numbers directly as they are and put them right into my ice table. Try it. Pause wherever you are. Pause and look up. Everybody. Hopefully you wrote out a Kp expression and you're not already cutting corners. Please notice that my Kp expression does not have brackets. Does your Kp expression have brackets in it? It shouldn't. These are not molarities. These are pressures. If I asked you on a test, which I will, to write a Kp expression and you included brackets, it would be marked wrong because brackets mean molarity. You must have the letter P for pressure. Okay. What's the problem?
It's negative.
Okay. Does that mean that we did our graphing wrong? No. It means we made the wrong assumption about which way it shifts. That doesn't come up very often, but it does happen.
Excuse me.
Ladies and gentlemen, beyond this slide, there are 2 more practice problems which I'm not going to take the time to do, but you're welcome to do in your loads of spare time that I know you have. I do, however, want to do this one because it is from your homework. And it's an even one. Woo! Woo! Yay! So many. So, here we go. Ready? It says, for the reaction below, Kp equals this number. Well, what I would do before you read any further is write the Kp expression for this reaction that is in yellow. To refresh your memory, what state or states of matter are permissible in a Kp expression? Gases only. Don't use brackets. Don't you dare write brackets. That's it. Why is the expression so short? They're solids. Okay. And they gave us a number. So, ladies and gentlemen, since the Kp expression is just the partial pressure of one gas, that number is the pressure of that gas. Okay? Alright, now let's look at the rest of the problem. A 20-gram sample of calcium carbonate, I'm going to write it above here, is put into a 10-liter container, that's a volume, heated to 800 degrees. What mass of calcium carbonate will be left in the container? The gist of this is, guys, I have information about the gas and about this reactant. Do you think some stoichiometry is going to be involved here? Yes. Okay. Think back to last week or maybe even the week before that. What is a big question you should be asking yourself right at this moment?
Is that STP?
Is it at STP? No, it is not. So what must I use? Pivnert. Now, ladies and gentlemen, let me just say something before I let you go off on your own. Pivnert is the ideal gas law. Don't you dare try to plug in something for a solid into the ideal gas law. You take it from here. Final topic for this chapter should be pretty easy. You did it in Chem 1. The Chatelier's principle. Ladies and gentlemen, this is a very formal definition, but the gist of Le Chatelier is if you have a system at equilibrium, it's nice and happy at equilibrium, and then you come along and you mess with it in some way, you are going to disrupt, shush, you are going to disrupt that equilibrium, but the reaction will always get back to equilibrium eventually. I mean, it might not take place in 30 seconds, but it will always eventually get back to equilibrium. And guys, there are 3 ways that you can mess with a reaction. And the first is by changing something's concentration. Put in more simpler terms, you either add or remove some part of the reaction. That is one way to mess with something. So let's look at this example. And let's say I have this nice happy little equilibrium. That's what a double-headed arrow means. Let's say I add some extra arsenic oxide here. Okay? Think back to Chem 1. If I add more of this reactant to the situation, in which direction will this reaction shift to restore equilibrium? To the right. Systems will shift away from an added component. Think about it. We've got too much reactant now. I need to use some of that reactant up to restore equilibrium. What if I do this? What if I remove some of this gas right here? It will shift right again. Things will always shift toward something that you have removed. Alright, let me just do one more just to make sure that you've got it. What if I remove one of my reactants here? Which way will it shift? It will not shift to the left. It will not shift to the right. Why? Ding, 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 ding.
Ta-da!
Ho-ho! I got you. This is changing concentrations. Think about when you write a Kc expression. What are the 2 states of matter that you include? Aqueous and gases. You exclude solids and liquids. So if you make changes to any solid or liquid, there is no effect. Now, the second way to change a system would be to change the temperature in the room. Now, this one is sort of special. I cannot ask you a Le Chatelier's principle question, like, is it going to shift to the right, the left, not at all. I cannot ask you that question when you're changing the temperature unless I tell you whether the reaction is endo or exothermic. Now, I know we have not talked about that much, if at all. And we are about to. The next set of chapters we're moving into it's the thermochemistry section. Okay? You should be familiar with those words, though. Endothermic means energy or heat is required or absorbed for a reaction to move in the forward direction. Okay? Let me say this again, in case you missed it the first time. You cannot answer a Le Chatelier's question involving temperature unless I tell you whether the reaction is endo or exothermic. So how am I going to tell you? Well, I could simply say, this reaction is endothermic. Pretty clear, right? Okay? Or I could give you a change in enthalpy. That's what this is. Don't worry about that word for the moment. Okay? a change in heat value, and if that value is positive, that tells you it's endothermic. Here is a third way I could tell you it's endothermic. If endothermic means heat is required, heat is absorbed, does that sound like heat is more like a reactant or a product?
Reactant.
Okay? So sometimes you'll see the word heat or energy written in on the reactant side. That's another way of telling you. So let's say I come along, I've got this reaction, I know it's endothermic, and I'm telling you we're going to raise the temperature. Turning the heat way up in a room. Does that sound like adding heat or removing heat? Okay? Well, where is heat? Here it is. You're adding a reactant. Which way will it shift? It will shift to the right. If something says that you're lowering the temperature, you turn the air conditioning way up, it gets really cold in here. Lowering the temperature is equivalent to removing heat. Where is heat? Here it is. I'm going to take some out. Which way is it going to shift? Okay. You guys just want to do the rest of the chapter by yourself?
No.
Okay, because I'm not done. Thank you. I got it. Thank you. Okay, here's another one. This one is not endothermic, it's exothermic, which you would have to be told that. Maybe I give you a delta H value that is negative. Maybe you see the word heat written on the product side. You tell me. I'm going to turn the temperature way, way, way down on this second reaction. What's going to happen? It's not endothermic, it's exothermic.
Yeah.
Shift right, shift left, not at all.
Right.
Shift to the right. Lowering the temperature means removing heat. Where is heat? It's a product. That's like removing a product. And let me give you a real life application with this that I think is so neat. Okay? Let's say you own a factory that manufactures a chemical, and you manufacture sulfuric acid and nothing else. That's all you do all day. Okay? That happens to be a very exothermic reaction. If you own a factory and your entire business is just to make lots and lots and lots and lots of this product, this sulfuric acid, is it in your best interest to keep your factory at room temperature, hot, or keep it cold? Why? It's cold is the answer. Think about it. If you keep the temperature of your factory very, very cold, that's the same thing as like removing heat. That would cause you to make more product, and that's your whole goal. That's your business. And that's a true statement, people. Sulfuric acid plants are kept at cold temperatures. The third way to mess with the system, we've got changing the concentration, changing the temperature, changing the pressure is the third. And I want to jump right to some examples. All right, let's say I'm going to increase the pressure in the room. Listen very carefully to how I say this. If you increase pressure, a reaction will shift to the side with fewer moles of gas. How are you supposed to know how many moles there are? I haven't given you any numbers.
The little numbers on the side.
The little numbers on the side. Coefficients. That's correct. This has a coefficient of 1. 1 mole of gas. How many moles of gas on the left-hand side of the arrow? Okay. So which way will this shift? To the right. How about this example? Okay, we got 4 moles on the left. No shift.
No shift.
How about this one?
Right.
Okay. Be careful.
Well, no shift, because it doesn't have any.
Be careful.
Is it no shift? It doesn't have any gas left.
It shifts. It
Right.
does.
Right. Right.
How many moles of gas are on the right-hand side?
0.
0.
Oh man.
6 moles on the left.
Well, actually, it's not very
Okay. So, if pressure goes up and you move to the side with fewer moles of gas, what happens when pressure goes down? Go to the side with more. Here's a cute little way to remember this. It's not really that cute, but okay. Most of you in here are juniors. Would you say the junior year is a stressful year?
Yeah.
Okay.
Yes.
For those of you that are seniors, you're applying to college, also stressful, yes?
Yes.
I'll just go with me on this.
Okay.
All right?
I'm not going to.
Would you say that pretty much everybody in this room is under high pressure? Okay? Just wait for it, I'm not done. I don't know about you, you may disagree, but when I feel like in my life that I have a lot of pressure on me to do something, I don't like to be around a lot of people. I prefer to be around fewer people.
This is a chem class or a coffee class?
I know. When the pressure is low in your life, think summertime. You're not in school. You don't have to worry about classes, etc. Pressure is low. I don't know about you, I feel pretty social. I like to be around people. I would like to be around more people. Alright, I'm going to throw you a curveball. Are you ready?
I'm always zigzag.
Yes.
What?
What?
Isn't it inverse related, so it's like a reverse?
Volume.
Yes, directly.
Increasing the volume means
Less pressure.
decreasing the pressure.
Oh, lay.
So it switches.
So it goes to which side? The side with
Size more.
more.
Don't.
Whose law is this? Boyle's law. Okay? So, ladies and gentlemen, to wrap this up, are you ready? Overall pressure of a system is increased. Equilibrium shifts to the side with less moles of gas and vice versa. Changing a volume is essentially changing a pressure. That's Boyle's law. And can anyone tell me what this word means?
Not moving.
No, it does not mean not moving.
Non.
A non-ert. No, wrong. Somewhat of a synonym, good SAT word, might be innocuous,
That's poisonous.
harmless.
Oh.
Innocuous means harmless.
Oh, no, yes.
Inert means a gas that is going to have no effect. A gas that's unreactive. Okay? For example, let's say to this first reaction, I decide to put into the container some neon gas. Is neon even a part of this reaction?
No.
No. This is an inert gas. It would have no effect. No shift.
So if you see something that's not in a reaction, it's just a no shift.
It's an inert gas, no effect. And ladies and gentlemen, that's all she wrote.